we've brought in one of our subject matter experts, Bryan Vining. Is it Vining or Vining?
It is Vining.
Vining. I keep saying that, but then I keep questioning whether or not I've lost my mind. So we've brought in Bryan Vining. He's one of our subject matter experts. I don't want to steal his thunder. We've all heard of PFAS in water. There's a new concern with PFAS, and I'm going to step aside and let our expert kind of take the wheel. And I would encourage everyone to ask as many questions as possible, or as many questions as you have. It's fantastic for us to be able to be involved with everyone and to get some feedback. It helps us learn how to improve this conversation and improve this as a talking point for other companies all over the country. We've already seen a little bit of interest in it, but nevertheless, it's coming. This problem is coming our way, so it's better to get out in front of it. Bryan is available I don't want to say anytime you need him, but if you want to set up some sort of conversation,
how about that?
yeah, if you want to set up some sort of conversation with me and Bryan, please don't hesitate at all to reach out. So without delaying any farther, Bryan, it's all yours.
All right. Well, thank you so much, Steve, and Jennifer as well for getting this all set up and inviting me to participate. I am very happy to be able to, talk with you all and tell you a little bit about what I see going on in the PFAS air emission arena. And really, although I have slides and I can kind of do this as a sort of typical lecture type talk, I mean, this is a small group. It's a lunch and learn. I feel like, I heard the word informal earlier rather. So I feel like informal applies. So although I've got slides and I'm going to be talking, I do feel like, if you want me to expound on a particular point, you don't have to wait to the end. Now, you can wait to the end also, obviously. I will have some time set aside for questions and whatnot. But anyway, I just wanted to say that because had we done this in person, I might not have even had slides, but having a virtual event without one wouldn't make a whole lot of sense. So with that as the intro, I'll just add that it is Vining, and that was always really useful back in the days before you could tell who was calling you on the phone, because if they asked for Mr. Vining, I'm like, nope, he's not here. So anyway, all right. So yes, as Deacon mentioned, I'm with the laboratory division of Montrose, which is Enthalpy Analytical. And in particular, I'm the lab director for the Wilmington, North Carolina laboratory, which focuses on ultratrace analyses. So these are compounds that are of environmental interest at the part per trillion level, usually because they're not only toxic, but they're bioaccumulative and persistent, so they last for years in the environment and typically in the body as well. So over time, small amounts become large amounts, biomagnification, they call it. So PFAS falls into that category, as does dioxins, PCBs, PAHs. There's a host of those. They're in the Stockholm Convention, and PFAS has been included in the Stockholm Convention now. So that's what we focus on here. And a few years back, we got into the PFAS testing in general. So we do not only some PFAS testing in air, but soil, water, and a pretty wide variety of matrices of all different sorts. We get things like sunscreen and ski wax, dental floss, pots and pans. We've seen all kinds of crazy stuff come through the lab looking for PFAS. So, air seems almost a little conventional, really, even though there's not just a whole ton of people doing it. But so with that as an introduction, let's get into why there's interest in PFAS and what are some good things to know. So I've got this in 4 rough sections or categories, if you will. Just a brief history. I don't want to spend a lot of time on what PFAS is unless there's questions there, but I think most people probably know about these compounds that are working in the environmental field at this point. But you might not be as aware of why there's some concern about PFAS in air. So I am going to talk about that a little bit. And I'm going to get into a very high level view of OTM45. It is like method 23 and a few other methods, a sampling and analysis method. So it covers both aspects. So I'm going to talk a little bit about both of those. And then I'm going to wrap up with some limitations around the method, as well as expectations that you should have of the method if you go to do implement it, or really just almost any PFAS and air measurement, whether it's strictly OTM45 or not. But there are some particular features of OTM45 that are important in terms of what you should expect. Okay, so brief history of PFAS. I have PFOA pictured here on the slide. That's perfluorooctanoic acid. So these are sometimes called forever chemicals, and we'll get into that a little bit more. I mentioned they're persistent. They do tend to last in the environment for years, possibly decades. It's not totally clear exactly how long they last, but we do know it's years. So first of all, PFAS stands for, it's an acronym, stands for poly and perfluorinated alkyl substances. So kind of the easiest way to think about it is these are a lot of the things you would find in oil and gasoline if they were typical hydrocarbons. Whereas with PFAS, what's happened is a majority, or as the case may be, all of the atoms that would be hydrogen in a hydrocarbon are now fluorine. And if it's a perfluorinated molecule, that means every bond that's not to a carbon or an oxygen atom is to a fluorine atom, basically. So that's important from a chemical perspective as well as from an environmental perspective, because the carbon-fluorine bond is an especially strong bond, and that makes it difficult to break. And this is why PFAS are known as forever chemicals, because they don't degrade quickly. They last for years, and that's fundamentally the reason why. So the more fluorine atoms you've got in this molecule, the tougher it is. And also, to some degree, the longer it is, the tougher it is. So these chemicals have been around a very long time. So the first experiments with these were all the way back in the 1930s. Teflon was developed, not necessarily with that trade name, but the underlying chemistry goes back 80 years. Then quickly from there, a host of useful industrial applications for these compounds were found. Things like non-stick coatings on pots and pans, waterproof fabrics, stain-resistant carpet. You know, these things are absolutely everywhere. PFAS was great for the coatings as well as firefighting foam, and I'll talk about that more in just a sec. And then PFOA is used for protective coating. So PFOA is perfluorooctanoic acid, PFOS is perfluorooctanoic sulfonic acid. And historically, carboxylic acids and sulfonic acids were the most prevalently used PFAS compounds. And they could range from 4 to 14 or even more carbons, and actually they can be as small as 1 carbon. Most of the attention is in the 4 to 14 carbon range, but you should know that there can essentially be any number of carbons, but people are not too worried about the ones that are really long, and that's mostly because they're not particularly water soluble and they don't transport nearly as well as the smaller guys. So that's why the smaller molecules tend to get more attention. Now, from the 1930s and 1940s, more and more uses for these compounds were found. So they became more and more prevalent. And those uses included things like I've already listed, and a real kickstart or leap forward, if you will, came in the early 60s when the Navy started looking for a better firefighting agent than what they had at the time, because obviously ships have a lot of oil and oil-based products on them, and aircraft carriers even more so because they've got jet fuel. And so putting out the fires could be really tricky. And the best agent for that is something that will essentially form a film on top of the hydrocarbon, and then water sits on top of that. And it turns out that so far, no one has found anything that does that better than PFAS. So for a long time, the military, as well as civilian firefighting agencies, used PFAS in firefighting foam. So, odds are pretty good that most fire stations around this nation and probably around the world have a PFAS issue, and they don't even know it yet. So certainly the DoD does. They've spent a lot of time and money understanding what the problem is and trying to work on it. Air Force bases in particular have a lot of PFAS contamination to deal with, and the DoD committed in the early part of the last decade to get rid of as much of the PFAS as they could. And that, to a large extent, is what has really taken PFAS to the next level. You had that, and then you had EPA looking at it in drinking water starting in 2012. And, now everybody knows about PFAS. So, okay, they last a long time. They've been used for a lot of things. They're essentially everywhere. Odds are good that right this minute you are wearing, sitting on, walking on, touching, or eating something that has PFAS in it, or on it, or both. And odds are it's more than one thing. Pretty good odds that if you're walking on carpet, it's got PFAS. Very well might be in your clothes, might be on your food wrapper. It could be anywhere. And because it's everywhere, and they're persistent, and their bioaccumulative toxicity is a real issue. And these compounds are indeed toxic to various degrees and in different ways. So, for example, the list of different types of toxicities includes reproductive toxicity, possibly cardiovascular, and endocrine disrupting type effects, carcinogenicity, that is, has definitely been linked to prostate cancer. It might be linked to some others. There's also liver toxicity and a host of other toxicities. And, the devil's in the details there, because it really becomes difficult to try and pin down the toxicity of any one particular PFAS a priori, that is, without doing a lot of studies, because as it turns out, PFAS have many different modes of toxicity in a molecular sense. So dioxins and PCB congeners, for example, all bind to one particular receptor in the body, so they all have the same mode of toxicity. That's not true for PFAS compounds. They're all over the place. And the compound that's most toxic to liver cells is not necessarily the same compound that's the most carcinogenic. And that's part of the reason that there's so much attention on PFAS, because it's very difficult, maybe arguably impossible, to nail down what the scope of the toxicity might be. You know, there've only been at most a couple dozen compounds whose toxicity has been studied well enough to say a lot about it. And of those, we know that there are multiple different toxicity modes and different ones are more important. And meanwhile, we also know that there are literally thousands of PFAS chemicals that exist whose toxicity is not understood at all. Now, we may be in the best case that PFOA and PFAS are the worst chemicals there are amongst all the PFAS chemicals, and we already know what they do in terms of toxicity. They're the most studied compounds. And if that's the case, then whatever you think of the situation, it's not the worst case. But we don't know for certain that there's not some PFAS compounds out there that are not, in fact, worse than PFOA and PFAS. And so this is why PFAS in general have gotten a lot of attention. And it's also why EPA has gone back and forth about regulating PFAS as a class of compounds. So that's really a complicating factor in dealing with PFAS. So you would think, okay, they're everywhere. They've been in use for decades. They're toxic and we know it. They're persistent. Surely there's some regulation. And as you can see from this slide, not really. This slide is blank because that's what there is to say about PFAS regulations at the moment. It's a little bit of an exaggeration. Some states have put some teeth into limits on PFAS emissions of various sorts, effluents. A couple of states are even trying to put levels in for air emissions, but these are still early days, and a lot of states have no regulations at all, no limits of any kind. And where you do, there are literally factors of 1,000 between one state and the next as to where those limits lie. So very little in the way of actual regulation, and what attempts there are by individual states to put limits into place are all over the map in terms of what concentration. Places like New Jersey, they're down below 10 part per trillion for the 6 compounds they think are the worst, whereas there are states that have limits of 1,000 part per trillion. So I say a little bit tongue-in-cheek that there's not much to know about regulation, because in point of fact, most states do have something about PFAS, but they're not really laws. They're simply initiatives being taken by the individual state environmental regulatory bodies to try and set some kind of limits on these things. obviously the best answer there is for there to be federal regulation, because then we can get everybody on the same page in terms of there needing to be regulation and what that regulation should look like. But, even in a case like this, where there's not just a whole lot of debate in Congress that regulation needs to happen, it's a slow process. So we're getting there. There was a PFAS Action Act passed very recently by the House of Representatives. Last year's Defense Reauthorization Act had a number of PFAS-specific requirements in it and monetary set-asides to address specific problems related to PFAS. So it's not as if Congress is doing nothing. But the PFAS Action Act is notable in that it actually would require EPA to promulgate regulations. And that is a step forward that has not happened before this year. So now that's passed the House, still got to go through the Senate, and who knows what will happen with that. But it is getting a lot of attention, and I think regulation is probably not so much if, but when. Okay, so big picture on PFAS is, they've been around forever, they're everywhere, they're toxic, but we're talking about manufacturing, right? So why are we worried about them in air? Well, because they're in the air. So this is an example where the state of North Carolina has been looking at PFAS in the air by collecting rainwater and analyzing that rainwater for PFAS. So this is an inferred kind of amount as opposed to the direct measurement of emissions that we're going to be talking about in a minute. But it gets the point, right? There are, in fact, PFAS compounds in the rainwater, and that means it has to be in the atmosphere. And in this case, I've shown a slide from just a little over a year ago, where you can see that where my lab is located in Wilmington, North Carolina, there was measurable PFAS in the rainwater. So it's in the air. That's why we're worried about it, because if it's in the air, it can move, right? We all know this. Once a pollutant's in the air, wind currents can carry it. It ends up on the ground, in nearby water, and that can be either wet deposition, i.e. the rainfall I was just talking about, or dry deposition on particulate matter. And once it's in these other places, well, then it's available for uptake by various organisms, so including people. So there's a problem that it's in the air. And that has been well established at this point. There's not really any debate that it gets into the air and that air deposition is an issue. For example, there's a recent study looking at a fluoropolymer manufacturing facility where there were compounds that were specific to that facility's process, PFAS compounds found up to 48 kilometers away. And that's not the first finding of this sort. There have been several here in North Carolina. The state did some examinations, as well as some universities looked at some samples and saw that the Chemours facility in Fayetteville was emitting PFAS into the air, and they were able to find those compounds, again, many miles away from the facility. And some of that included the river, the Cape Fear River, next to where the plant is, and which runs down to Wilmington. So between the air deposition and what the plant was putting out, some of you may remember about 4 years ago, Gen X in the water in Wilmington was a big deal. And we had already established the lab here, and we actually had no idea that that was going to become a thing when we created the lab. So fortuitous in one sense, because here we are sitting in one of the hot zones for PFAS in the United States and probably in the world. So we know it can move with the wind, which means if it's a briskly windy day, it travels fast. It can travel many miles, as I said, up to 48 kilometers. And of course, the deposition is going to go with the prevailing winds. So typically one part of the nearby area will get hit harder than the others, but wind does move around, and so you will see PFAS deposited all around a facility. And those levels can actually get to be pretty significant. In the study that I'm referencing here, there were levels over 1 part per billion in nearby surface water. So that's why we're worried about PFAS emission in the air, because we understood industrial effluent into rivers was an issue, but the understanding that emission into the air could also be a significant root of pollution is more recent. And that brings us to OTM45, which is the method put out 7 months ago now in January for examining PFAS in point source emissions. So that method borrows some principles from method 23 and from the EPA method 533, which is a drinking water method for the analysis of PFAS, as well as a wealth of experience from both individuals at EPA as well as various stakeholders, and put together a method that attempts to address the need to measure PFAS in point source emissions. So this is a schematic of an OTM45 sampling train. For those of you that are familiar with MM5 or M0010 method 23 type trains, this will look rather familiar. One thing I like about this, and this particular diagram comes right out of OTM45, is you get some color coding of different fractions of the train. And one of the first things that might stand out is that there are 2 XAD modules in this train. So you've got one up at the front where you're used to seeing it, but then you also have one after the last water impinger and before your silica gel impinger that is intended to measure and capture any PFAS breakthrough from the impingers. Now that particular part of it, that breakthrough XAD trap, may not hang around long term. We don't really know. It depends on how much breakthrough is observed. My experience thus far is that breakthrough tends to be pretty limited, if any at all. But we have a lot of data to collect before we can, as a community, decide that the breakthrough trap is not necessary. So at the moment, EPA is still wanting to have that breakthrough XAD module. Other than that, it actually looks very much like a method 23 or typical MM5 train. You've got a filter, XAD, several impingers, and there was also some concern that Teflon components and fluoropolymer components in the sampling train might be an issue. And OTM45 does have something to address that. And so, as one would expect for a method like this, there's a requirement for a field blank. That field blank is actually connected in the sampling train. And then you perform the typical leak test type scenario with sampling glassware that has already been used to collect at least one live sample. And then there's a proof blank, so-called, which is exactly the same thing as the field blank, except that glassware that has not yet been used to collect a sample is used to generate the proof blank. And then you have a trip blank, which is also a full set of sampling media, but those media are never attached to or integrated into the sampling apparatus. They're simply sent out into the field with the rest and they come back, but they're never opened up. And so in this way, EPA has attempted to make sure that there's an ability to tell or to distinguish, if you will, between background that's picked up just by, being shipped around wherever the sampling media are being sent versus, say, contamination that's coming from a filter holder or an O-ring or the like versus contamination coming from used glassware. So I think in that respect, OTM45 does a very good job of looking at potential sources of contamination. And there again, from what I've seen, the sampling train components don't typically appear to be a big source of contamination. Now, one important thing to say there, though, is that just because it's not usually doesn't mean it won't ever be, right? So one does need to be a little bit careful, not to be too cavalier about that. If someone were to ask me what would I recommend, I would recommend that, if you've got some components because you've done some PFAS sampling, these components have not previously given you any issues, I would make sure that those are the ones you use when you then go to do some sampling. We do similar things in the laboratory where we know that we have certain vials, certain caps, certain gloves, these kinds of things that we know work well for PFAS analysis, and we make sure we're only using those and to the best of our ability. Although in the days we're in where supply chains are a little crazy, we don't always have as much control over that as we would like, and you might run into similar issues. So another thing that's interesting or a little bit different is that the temperature at which the apparatus is kept is rather important, in particular the nozzle, because there are a class of compounds that are going to be looked at. They're polyfluorinated ether carboxylic acids, PFAS, of which Gen X is one. And those compounds can readily decarboxylate in the gas phase to produce ethers, and at relatively low temperatures. So for example, with Gen X, I believe the conversion point is 248 Celsius. I might have that not quite right, but somewhere in that ballpark. But OTM45 does address that, and it tells you, to keep your sampling temperatures below that threshold so that you do not get that breakdown. And that's a known breakdown. What we, of course, don't know is any other breakdowns that may happen. So apart from those things, a test for PFAS air emissions will look a lot like a method 23 or M0010 type analysis or sampling event. You're going to pull a certain amount of air for a certain amount of time, certain flow rate, etc. And the exact amount of time that you're going to want to pull is going to depend on the detection limits you're aiming for. It's all pretty standard stuff if you're used to doing these types of sampling events. Now, as I mentioned, and as the diagram shows, you've got 7 different components that get sent to the laboratory. And OTM45 has a pretty detailed breakdown of the solvent recovery, the sample recovery procedure. One note I would make is that the method calls for several rinses that use methanol with 5% ammonium hydroxide in it. And the reason for that is that we know that the compounds are more stable in basic methanol than in just regular methanol with no additive. That was why EPA put the ammonium hydroxide into the method, and that's great in principle. I think probably 5% is overkill, but that's what's in the method. If you are in a situation where you're going to do sampling and you have 5% ammonium hydroxide, you want to generate that in the field, and preferably somewhere with really good ventilation, and get that stuff outside ASAP. It is a bit of a safety concern because 5% ammonium hydroxide is really powerful, and you will definitely notice it when that jar or bottle gets opened. Can't miss it. So anyway, there is that. So there's some rinses that are getting done as you would expect. Filters getting put away. Again, very simple, standard stuff relative to what you would expect from an MM5 type train. So those fractions get sent to the laboratory, and then in the laboratory, we're going to combine some of those so that we then have 4 analytical fractions. So the 7 sampling train fractions become 4 analytical fractions, and I diagrammed that out here on this slide. You got a front half, a back half, impingers, and the breakthrough X80. And that's the way OTM45 has it broken out. Again, I think that's probably more from a trying to understand how things are working perspective than from a perspective of you need that to properly characterize the emissions. I mean, from understanding what the emissions are, you probably only need 1 fraction, maybe, combine everything basically. Maybe you'd want the breakthrough extra though, because otherwise it doesn't really tell you much. But at the moment, the way OTM45 is written, we got a front half, we got a back half, we've got impingers, we've got the breakthrough X80, and where you're going to see individual PFAS compounds will depend to some extent on their volatility, as well as their tendency to adhere to the filter or the X80 or what have you. And most of the time you're going to expect to see most of the PFAS in the back half fraction. And to date, most of the data I have seen conform with that expectation. Now, that's not to say you won't find things in the impinger or the front half or even the breakthrough. There are situations where you will find PFAS compounds, even the same PFAS compound in all of those fractions. But more often than not, you're going to see the bulk of it in the back half. So that's OTM45 in a very, very high level nutshell. And again, I kind of designed to leave some time to talk about things. So what is it? It's a method to gather information. It's a starting point. It's literally better than nothing, which is what we had before. But it's not a regulatory or compliance method. It's not the final word by any stretch of the imagination. And EPA says as much as well. A lot of this is to gather information so that we really know what we need to do. OTM45 is probably not going to be, the method 10 years from now for this. But it is a reference point, and a lot of people who are interested in PFAS air emissions are talking about OTM45. So I'll wrap up real quickly with some limitations and some expectations that you should have. We don't have a lot of cleanups on the laboratory side, and sample matrix interferences can be a real problem for air samples, especially on those back half samples. You tend to get more matrix interferences, and this can really mess with the analysis. And on a practical level, that may do more to affect your detection limits than anything else. However, another major concern is that XAD resin has a significant amount of PFAS in it inherently. I don't really know the manufacturing process and why we would have a lot of PFAS, but we do. Now, my laboratory buys a certain grade from a certain manufacturer, and we have our own process for cleaning it. And everything I've heard and seen suggests to me that our process is working about as well as anyone expects. But we do not generate perfectly clean XAD, and I don't know that anyone can in any realistic scenario without it costing a ridiculous amount of money and perhaps destroying the XAD. But that can limit the detection limits achievable for certain compounds. And, it's something that you want to think about if you need to get into a PFAS air emission sampling job. And lastly, there's just so much we don't know. That is a limitation. There's a lot we don't know. So we are, to a certain extent, shooting in the dark. And that's why EPA put this method out to some extent, is so that we had some sort of a standard to start learning from. Now, if you're doing a sampling program for PFAS and air emissions, you can expect that it's going to be a little expensive, right? Every train is 4 samples in the lab. Every one of those fractions has to be extracted and cleaned up and analyzed. So it is not a cheap analysis. That's one thing you should expect. Also, with 4 extractions for every sample or for every train, it's not something that gets turned around super quick either, because again, now every sample requires 4 different extractions, and they're different extractions. So the XAD will get extracted one way, the filter maybe the same way, maybe not. And the impingers definitely don't get extracted the same way. So there are some differences in how the extractions are done and how much cleanup is necessary. So that's going to take some time, and consequently, with all of those data, you're going to need to plan to spend a little bit of time looking at the data, because for every train, you're going to have a minimum of 4 results for every compound, and you're going to have to decide how you're going to deal with non-detects and what different things mean. So with that said, I will wrap up there, and I'll leave it open to questions and discussion.
Thank you, Bryan. That was awesome.
Thanks.
If I certainly have some questions. For some reason, I got a bad echo too, but
fire away.
So I previously also worked with a company that produced a PTFE product, a Teflon product. So I'm pretty familiar with a lot of that stuff. So I'm gonna throw you some softball questions, right?
Okay.
So, well, first let me start off with, you mentioned cost is high, right?
Yeah.
Producing that stuff is certainly expensive. Also, I think we would all agree that cost for some sort of repercussion would far outweigh some sort of cost for initial testing, right? I mean,
Oh, sure.
yes, it is expensive up front, but being able to get out in front of that stuff, I think is worth it when you take a look at what it costs on the backside. I mean, would you agree with that?
Well, certainly if you're in a business where you're using or making a fluorinated product like that, because I mean, I can tell you on the lab side, again, earlier on I mentioned there's not a lot of regulation, but there's a lot of business. And the reason there's a lot of business is everyone's worried about liability.
Yep.
So I think you're onto something there that, a lot of folks are looking into this because they'd rather spend a few thousand or tens of thousands than get hit with $1 million lawsuits down the road.
Plus black eye for the company as well.
Very much so.
So if you have an issue with PFAS, if you have an issue in water, can you assume that you probably have some sort of issue in air as well, or are those two uniquely different to the tune of we have no idea?
So
or is there a correlation?
I think what I would say is that if you have a problem in water, you need to think about whether you might have a problem in air.
Okay.
So it's not necessarily that there will be one, but there might be. And where that comes in is what's the process that's leading to the PFAS contamination. For example, we've got a lot of clients that are wastewater treatment plants, right? So in principle, they shouldn't be emitting much PFAS into the air. I won't say none, but you wouldn't expect a whole lot there, right? But one of the things that we know is that wastewater treatment tends to oxidize the influent, and oxidation can actually convert some PFAS into the so-called terminal compounds, which are the carboxylic acids and sulfonic acids I mentioned earlier. And those are known to be toxic. So you can actually get more toxicity coming out of a wastewater treatment plant than you had going in. And we've actually seen that in some samples that we've analyzed. So probably not an air problem, but definitely a water problem. So, but then, as I mentioned, there's the case of a fluoropolymer manufacturing facility where they definitely were contributing to both air and water. So it's definitely something that if you see it in water, you should be thinking about whether you have it in air.
All right, I got two more. If you have an issue, is it something that you can work toward cleaning up? I know that may be outside of your expertise, but I think you, just based on your experience, you've probably got some sort of I'm familiar with the water issue. I would, right here is where I would normally plug Montrose's ECT2 group.
Right.
But with regards to air, is there a cleanup process out there, or are we still in that? Are we still in discovery phase of that?
We're very much in discovery phase. So there are some things that one, I guess I would say, could try. So one fairly simple, theoretically, not practically, theoretically, fairly simple, is to increase your combustion temperature if you're doing combustion. Because there is some evidence that if you get the temperatures high enough, you will get rid of a lot of the PFAS that people are looking for. That's how I'll put that. That doesn't necessarily mean that you don't have any PFAS coming out. It just means the ones that people are looking for may not be there. And that is actually one of the open questions with air emissions in general. Now, another thing you could look at is, you might get some benefit from your typical, calcium lime type scrubber, because there are acids here. So that may help. And certainly you could think about having some sort of granulated activated carbon filter in your APC, but I don't know enough. That's where we start getting out of my expertise, and I don't really know what's available out there or not. Now, I will say I know that there are entities that are looking into that very issue and looking at ways to try and clean up emissions.
All right. If anybody has more interest in that, reach out to Deke. We will figure it out for you, right?
There you go.
All right. I don't want to take everyone else's time. Does anyone else have questions for Bryan? He's a wealth of knowledge. You managed to answer every single question that someone had. That's incredible. Well, right. So one last one. Any expectations on enforcement time?
So sure. In the short term, that's probably going to be state by state. So I mentioned somewhere along the way that there are a couple of states that are talking about implementing limits for air emissions.
Okay.
Michigan is one. I'm trying to remember who the other one is.
I think we're doing a project with New Hampshire.
Yeah, that would make sense.
Maybe California.
Yeah. So you're going to see some limits from individual states. I think by virtue of the fact that OTM45 just came out earlier this year, one can reasonably expect that the federal government is several years, probably something like a decade from any sort of enforcement. That would be my guess. Now, having said that, that also depends on the political pressure, right? Because there is a lot of concern about these compounds, and if the already reasonably high political pressure gets more intense, then that might accelerate the time frame. And I can tell you that in OTM45, reading the document, and knowing what I know, I could put together some things and see that in an ideal scenario, that document probably would not have come out as soon as it did.
Okay, gotcha.
The political pressures there.
Yeah.
So.
Well, I will say in my experience, those that get out in front and start working on a solution for the problem tend to get a little more leniency than those that react
sure.
to someone else's solution. So I'm proud of you guys working hard and getting ahead of this. I'm glad to have you on the team, man.
Well, thanks. Yeah, I mean, myself and several of my lab staff have long experience working with method 23, and we were already measuring PFAS, so it was kind of a no-brainer to move over into the PFAS air emissions measurement. And we'd been talking to folks at EPA for a couple of years now, 2-3 years. So it was no surprise when OTM45 came out. Other than that, it happened faster than I expected.
Okay. Jennifer, did you have anything? I think we probably listen. If you give a salesperson a microphone, you got to know we're going to go over the time limit a little bit.
That's okay. Everyone has stayed on, so obviously they're either got distracted and they don't know that you're ending. No,
they've got me on mute.
They've been paying attention, and you've answered all their questions, so thank you about that. If anybody does have any questions, I can send you Deke's information. He also has the list of people who registered. He may be reaching out to some of y'all and sharing more information with you. But I just want to say thank you to everyone that was here today. And we look forward to, I see Heather, I see your thank you in the chat. And that's really all we have today. So if you need contact information for Bryan or Deke, let me know. We'll be glad to share it with you. And otherwise, I will just wish you a good afternoon and say thank you again to Deke and Bryan for a great presentation. We really appreciate it.
Thank you so much. Hope everybody has a great day.